Okay, so let's solve our problem. Recall that it is good practice whenever a problem is given to you or a question is given to draft out the parameters in the question. So the tennis ball is projected horizontally from the top of a cliff. So if we have this sketch, this is our cliff, and the height of this cliff is 50 meters, and a velocity of, so the velocity with which the ball is projected is 10 meters per second. That is the initial velocity. Now recall that when a body is projected like this, the effective initial velocity only functions with respect to horizontal movement. It doesn't have any effect in its vertical movement. Once you're able to analyze and understand this, solving projectile problems become very easy. When you understand that this initial velocity only has effect in taking the body in horizontal direction, but doesn't have any effect in bringing it down. Why? Because the effective active force bringing it is that of acceleration due to gravity. It is gravitational pull that brings the body down. So as a result, this only has effect in the horizontal direction. So we are going to solve now. So I said from here we have it that h, which is the whole vertical distance, is 50 meters. Then our initial velocity is 10 meters per second. And it says find the time taken to reach the ground. So the first question demands for us to find the time with which it will get to this ground. And recall it is coming down. When we talked about equations of motion under gravity, we mentioned that as the body falls from a height to a lower level, acceleration due to gravity is positive. Therefore, our g here is positive and it is a constant, approximated 10 meters per second squared. Okay, so which of the equations of motion would allow us solve for the time taken to come down? If we recall the three equations of motion, we say that the first one is final velocity equal to initial velocity plus gt. Okay, the second one is height is equal to ut plus half gt squared. And then the third one, v squared is equal to u squared plus 2gh. These are the three equations of motion under gravity. So which one now best suits to solve this problem? If we look at this, the first one will not come in because it doesn't have room for us to impute the height. The second one has it, but okay. So it says here, the time taken to reach the ground. So the second one becomes very handy. That's the one we use. So we're having h equal to ut plus half gt squared. Substitute the values of these parameters. Here we have 50 being equal to. Now take note, this u, like I mentioned here, is only effective in taking this body in the horizontal direction. So in the vertical direction, u has no effect. So in that, on that note, u here is equal to 0. Take note of that. So we have 0 times t plus half, our g is 10 times t squared. So this will give us 50 being equal to, this will go off, 2 into itself 1, 2 into 10, 5, 5t squared. So this will give us, dividing both sides by the coefficient of t, or moving the coefficient of t squared to the other side, that will give us 50 over 5 equal to t squared. Therefore, t alone now is t squared. We will have it that 5 into itself is 1, 5 into 50 is 10. So t squared is 10. Where t alone now is the square root of 10. That becomes the time it will take for this body to get to the ground level. And this will give us 3 points. We punch that out. Square root of 10 is 3.16 seconds. That will be the time it will take for this body or the ball projected to get to the ground level. Again, what's the second question? It says, determine also the vertical component of the velocity when the ball hits the ground. Now, what is the final velocity as the ball hits the ground? Okay, we use this is our B, because this is our A. Also, at this instance, U is still 0, so we are looking for V, where we have H equal to 50 and G equal to 10 meters per second squared. So which of these equations would allow us to solve for V? Automatically, equation 2 is off our options. So we have this and this. We go for equation 3. Equation 3 will allow us to solve for that without considering time. So we have it that V squared is equal to U squared plus 2GH. If we go there, we have V squared equal to, recall U is 0, plus 2 times 10 times 50. So we have V squared equal to 2 times this will give us 1,000. Right? Okay, this is 500 times 2, 1,000. So our V now is, right? This is U plus 2GH. Okay, it's correct. So that will give us square root of 1,000. And here we'll have it that V is the punch, or the square root of 1,000. That will give us 31.62. What's the unit of velocity? Meter per second. So this becomes the final velocity of the ball projected as it drops to the ground level. The next question there says we should determine the distance from the foot of the cliff where the ball hits the ground. The distance. This is where we bring up the idea again that this initial velocity is actually effective in taking this ball to this distance. So this is the distance it will get to where the ball drops to the ground level. So the distance from here to here we are asked to find. So we are looking for S when U is 10 meters per second, and recall that acceleration is 0. There is no acceleration going on there. Alright? So the body is not accelerating. It is not accelerating. So if we now bring up the 3 equations of motion here now, the first one is V equal to U plus AT. The second one is S equal to UT plus half AT squared. And the third one is V squared equal to U squared plus 2AS. So which one now becomes handy? We see that we can actually solve with this. This would help us solve for that. Or this. Okay, the second one. Let's use the second equation. Already we've determined the time it will take to come to the ground level. But let's see. This becomes S equal to UT. Okay? S becomes, because A is 0, no acceleration. So we are using the second equation where S is equal to UT. Substitute the values. Our T already is 3.16. So S now would be U is 10 times 3.16. This is seconds. So that will give us 10 times this. You move your decimal point once. Because of this 1 0, that will become 1.6 distance is measured in meters. So the distance from here to here would be 31.6 meters. So far we've seen the time taken to get to the ground level, then the maximum velocity it attains vertically, and the total distance from where it was projected to where it landed. So with this, we've been able to tackle one problem under the projectile motion, where a body is thrown off from a height. When we now consider more on this, we see to it that projectile motion is not just observed from a height to the ground or from the ground to a height. It so happens that when a body is projected, it tends to move sometimes from where it is projected, which is at a lower level, to a particular height, and then back to that level again. Just for example, we have footballers. When a ball is kicked, it moves from the ground level, gets to a height, and then comes back to the ground level again. And we observe that this type of projectile motion is not just this simpler one we discussed now. So we need to note what happens with such projectile motion. How do we analyze the problems involved in this, and how do we solve them? First, we express a motion that tells about such a movement. If we have it that a ball is projected in this order, now we see that this ball projected makes an angle with the horizontal. If you observe, it has vertical components and horizontal components, so there is an angle it makes here. And this angle is very important in determining the maximum height it has reached, the time of flight, which is the total time it will take for this body projected from this point to come back to another position or another point, but on the same plane of projection. So, and then the total distance, which is the range. So the time it will take to come back here, the maximum height, and the range. These informations are very much important, but we will need to analyze this before we can solve for such challenges. And how do we do that? We bring back our knowledge on resolution of vectors, where this initial velocity u is resolved to its vertical component and then its horizontal component. So we'll resolve this u, initial velocity, to its vertical component and horizontal component with respect to the angle of inclination, its angle of inclination. If we draw this and call this our u, angle of inclination to the horizontal plane, we take up a parallel to this, where this is our y and this is x. Let's resolve this. If we still recall our SOHCAHTOA, we'll see to it that in this direction and direction, this is the hypotenuse and this is the adjacent. So if we are considering hypotenuse and adjacent, for us to get the effective value of u in the horizontal direction, we will have to involve which of these trigonometric ratios allows for hypotenuse and adjacent to be manipulated, and that is cos. So we'll be saying cos theta is equal to, that is u in the vertical direction. That will give us cos theta being adjacent, which is our u in x direction, all over u. Okay? But we are actually looking for u in x direction. So u of x becomes u cos theta when we cross multiply. So this is the effective value of u in the horizontal direction. Okay? And then when we consider the effective value of u in the vertical direction, y, we now consider this is parallel to y here. So we are using this side, which is the opposite and the hypotenuse. Opposite and hypotenuse sign comes in. So we say that sine theta is equal to opposite, or opposite now is what? U in y direction, which is u of y, all over hypotenuse, which is u. So get the effective value of u in y direction. That becomes u of y becomes u sine theta. So this is the effective value of u in the vertical direction. These are very important because we'll be substituting them when we will be resolving or determining the equations for maximum height, range, and time of flight. So as a result of this, if this is y, which is the direction of the projectile, because it must definitely get to a maximum height, before acceleration due to gravity will start bringing it down. First, it tends to reduce its velocity until it is 0 before it now starts bringing it down. Okay? Now, if we are to get this, recall that s is equal to ut plus half at squared. This is our basic equation of motion. But with respect to an object moving in a vertical direction, we now have it that h is equal to ut. Now it is moving up. Recall, while moving up, g is negative. So it will affect this minus half gt squared. Okay? Now substituting this now, y, since it is in y direction, this becomes y equal to ut minus half gt squared. But recall that the effective value of u in the vertical direction is this. Okay? So let's bring that in now. Y becomes u sine theta times t minus half gt squared, which we can finally evaluate as y equal to ut sine theta minus half gt squared. So this becomes the height the body will get to as we run off equation of motion. Okay? This becomes our equation of motion for the object with respect to y direction. But we don't end here because this has not given us the actual formula with which to solve for maximum height. So we will now take up how to determine formulas for total time of flight, maximum height, and then range. And that will take us to the next part of our learning. I wipe this, but still recall this expression because it is very much needed in determining this. So we're going to copy that out. We have y equal to ut sine theta minus half gt squared. First, we want to get the time of flight. And what do we say the time of flight is? We define the time of flight as the total time taken for a projectile to come back to a new position on its plane of projection. When an object like we have it here is thrown, the time it will take for it to leave this point A, travel to a maximum height, and then come back to another point which is on the same level, the same plane of projection. We call this B. So the time it will take for it to travel from A to B is known as the time of flight. It's known as the time of flight. So how do we determine formula for this? When we talked about motion under gravity last time, I mentioned something to us that the time to travel from a particular level to a height and the time it will take to move from that height down to another point on that same plane of projection are equal. So that means the time it will take for it to move from here to H is the time it will take for it to move from H to B. We're going to prove this, but first let's bring back our equation. Here, the time of flight would now be taken as capital T. So from here, we have it that y is equal to u capital T sine theta minus half gt squared, since we want to determine the total time. But if you recall from here, y becomes 0 as the projectile drops at this point. The moment the projectile moves from here, gets to the maximum height where y is maximum, and then comes down, here y is 0, because if you extend y to this point, it is the 0 point. So y is 0 here. So if y is 0, then we'll have it that 0 equal to ut sine theta minus half gt squared. Now we are looking for t, so we're going to make t the subject of formula. But then let's evaluate this first. Since we've gotten a quadratic equation here, we can turn it back to a linear equation by moving this over, where we will now have 1 over 2 gt squared is equal to ut sine theta. Recall, we want to make t alone the subject of formula. This is dividing all of this. In other words, we have gt squared over 2 is equal to ut sine theta. So we can actually cross multiply. That will give us gt squared equal to 2 times this, 2 ut sine theta. Now we make all of this so we can eliminate one t. We can't have the t on both sides of the equation. To eliminate one t, let's make all of this the subject of formula. That's 2u sine theta. That will give us gt squared over t, which is the coefficient of this, is now equal to 2u sine theta. Where t here will run off one of these, remaining one, according to the laws of indices. So we now have gt is equal to 2u sine theta. T alone now becomes 2u sine theta all over t, all over g rather. This becomes the equation for time of flight. So our t here now becomes 2u sine theta over g. Now recall what I said here, that we can as well prove that the time to get to this maximum height is also equal to the time it will take to come down here. Alright? Twice of this would give us our t. So that means if we use this alternative method, where we have it that v is equal to u plus gt, recall t is going up. Okay? Sorry, the object is going up. Okay, this becomes minus. So we have it at maximum height, v is 0. So that will give us 0. And the effective value of u in the vertical direction is u sine theta minus gt. Now let's move all of this to the other side of the equation. That gives us gt equal to u sine theta. Therefore, our t now, okay, let's call this t1, since it is time to get to the maximum height alone. So t1 becomes u sine theta all over g. If twice of this gives us our total time, that is, if t is equal to t1 times 2, then we'll have it that t now is 2 times u sine theta over g, and that will give us t equal to 2u sine theta over g. So we see that the two expressions are the same. This has given us this an alternative way of getting this equation. The next one we get to solve now is for maximum height. H. We're going to derive an equation for solving for the maximum height when an object is projected up. Now, if we recall the three equations of motion again, V equal to U minus, since it is going up, GT, S equal to, okay, and now we are looking at H equal to UT minus half GT squared, and then V squared equal to U squared minus 2GH. Now we are going to consider it such that, recall that initial velocity doesn't have effect in taking the object. So we are using it with respect to final velocity being 0. So that would be V squared equal to, recall the effective value of U sine theta all squared minus 2G, because now we are looking for H, and H is capital H. So this becomes the equation to solve with. And at that point, we know that V is 0 at maximum height. V is 0. So it becomes 0 equal to, if we open this bracket, we have U squared sine squared theta minus 2GH. Let's move everything over to this side. This becomes 2GH is equal to U squared sine squared theta. Therefore, H alone now becomes U squared sine squared theta all over 2G. This becomes the equation for maximum height. With this, we solve for the maximum height the projected object has attained at an angle. Okay? And finally, the range. The range. We said that the maximum height first is the maximum vertical distance the projected object would get to from its horizontal plane. That gives us the maximum height. But here, the range is the maximum linear distance, horizontal distance, the object would reach to from its point of projection to a new point on its plane of projection. So, from this description here, the range would be the distance from here to here. So where it drops back to a point that is along the plane of its plane of projection. Recall that when we are considering its plane of projection, it is now horizontal. So we are considering the horizontal effective value of the initial velocity, that is U, where we have now that U in the x direction is U cos theta. Don't forget this, very important. And also recall that A is equal to 0, because we are actually using the formula that S is equal to, that is this, UT plus half AT squared. But here now, our S, which is distance, is taken as R, that's the range. Okay? So range now is equal to U cos theta T. Remember that the T here is the time taken to move from here to here. So it is the total time of flight. But already we've determined a value or formula for total time, and that is 2U sine theta over G. So that means we are going to substitute that into this equation. So our R now becomes U cos theta times, let's put in this value now for T, 2 u sine theta over g. Okay? We'll now evaluate. If we evaluate that, what are we going to have? We multiply through, where we now have this, and this will give us 2u squared sine theta cos theta. That's our r is equal to all over g. This becomes what we have. But from our trigonometric constants, in our trigonometric ratios, we have it that 2 sine theta cos theta is equal to sine 2 theta. Okay? Of course, we